we are going to learn another important topic of mathematics, that is multiple integral. We will have a question. What is a multiple integral? A multiple integral, the answer can be obtained by considering a function of more than one variable. Say we consider a function of two variables, then we can think of integration with respect to both the variables. Say we have got a function of two variables x and y, then we can think of integrating the function with respect to both x and y. Can we consider an integral like f of xy dx dy or f of xy dy dx? Does it has any meaning? We just answer this question. We have got so many types of uses for multiple integrals. We can use multiple integrals to find out area of a plane region. We can determine mass of a plane lamina, area of a curved surface, coordinates of the center of gravity, volume of a solid, mass of a solid, moment of inertia of a plane region or moment of inertia of a solid, and so on. They also find applications, or multiple integrals also find applications in topics like vector calculus, where we come across double integrals, surface integrals and volume integrals. One important point is we consider only definite integrals in the context of multiple integrals. That means there will be definite limits for the variables. Can we think of a mathematical representation for a double integral? How we represent mathematically a double integral and then a triple integral? Mathematically, we can represent a double integral, a general double integral, by double integral f of xy dx dy over the region R. A double integral will always be evaluated over a region of a plane. So R is the region of the xy plane. Then what is the general representation for a triple integral? Triple integral over V, f of xyz dx dy dz. What is V here? V is a region of space or a finite portion of space. To evaluate these integrals, as mentioned already, we need limits for the variables. So if we think of how an area or a portion of the xy plane is represented, then we will be able to know the limits. So how a plane region is described, or how a plane region R of the xy plane is described. This helps in obtaining the limits for the variable. A general region of the xy plane can be observed to lie between two vertical lines and between two horizontally oriented curves. Here, if the line at one side is x is equal to a, the line at the other side is x is equal to b, the curve at the bottom is y is equal to a function of x, psi x, and the other curve is y is equal to eta a function of x, then the region can be described by a less than or equal to x less than or equal to b, psi x less than or equal to y less than or equal to eta x. There is another way of representing the same region of the xy plane. Instead of observing that the region lies between two vertical lines and between two horizontally oriented curves, you can also think that the region lies between two horizontal lines and between two vertically oriented curves. If the line at the bottom is y is equal to c, the line at the top is y is equal to d, the curve at the left hand side is x is equal to py, the curve at the right is x is equal to qy, then the region can also be represented by the inequalities c less than or equal to y less than or equal to d, py less than or equal to x less than or equal to qy. What is the difference between these two representations? Although we can perform integration of a function of xy over the same region, depending upon the type of representation, we will be able to decide in which way we have to perform the integration. Suppose a has got constant limits, x has got constant limits, and y has got variable limits. Then for performing integration over the region R, we evaluate with respect to y first and then with respect to x. In the other representation, when x has got variable limits and y has got constant limits, when you perform the integration over the same region, we perform integration with respect to x first and then with respect to y. Then let us consider a rectangular region, a rectangular whose edges are parallel to the coordinate axis. Let one line, one vertical line be x is equal to a, another one is x is equal to b, a horizontal line is y is equal to c, another horizontal line is y is equal to d. Then the region can be represented by the inequalities a less than or equal to x less than or equal to b, c less than or equal to y less than or equal to d. Let us consider another example, how to describe the region of the circle x square plus y square is equal to a square. We know that the center of the circle is at origin. It meets the x-axis at minus a plus a. It also meets the y-axis at minus a plus a. But we cannot have the inequalities describing the region as minus a less than or equal to x less than or equal to a, minus a less than or equal to y less than or equal to a. Because if we write those limits, they describe a square region whose center is at origin. Now how shall we describe the region of the present circle? We observe that it lies between two vertical lines x is equal to minus a and plus a. It lies between two semicircles, a lower semicircle and an upper semicircle. Lower portion of the semicircle can be represented by y is equal to minus root a square minus x square. Upper part of the semicircle can be represented by y is equal to plus root a square minus x square. So the region can be described by the inequalities minus root a square minus x square less than or equal to y less than or equal to plus root a square minus x square, minus a less than or equal to x less than or equal to a. We can also describe the region in a slightly different fashion. We can also observe that the region lies between two horizontal lines and between two vertically oriented curves. In such a case, we can say that the limits are minus root a square minus y square less than or equal to x less than or equal to plus root a square minus y square minus a less than or equal to y less than or equal to a. In that fashion also, the same region can be described. Now, coming to another coordinate system, say polar coordinates, the same region of the circle can also be represented by means of the inequalities 0 less than or equal to r less than or equal to a and 0 less than or equal to theta less than or equal to 2 pi. Why the limits should be 0 and a for r and 0 and 2 pi for theta? We know that r is the radial coordinate. Radial coordinate means distance measured from initial point or origin in any direction. At origin, r will be 0. On the circumference of the circle, radial distance will be maximum, namely a for a circle of radius a units. So, r changes from 0 to a. Coming to theta, theta is always measured anti-clockwise starting from the initial line or positive direction of x-axis. From positive direction of x-axis to positive direction of y-axis, it will be pi by 2 degrees, pi by 2 radians. Again, proceeding in a similar fashion, when you proceed from 0 to 2 pi, we will be able to cover the whole region of the circle. So these are the limits in polar coordinates. Let us consider another example. The case of a circle having its center on positive direction of x-axis and passing through horizon. The circle I am going to consider is x square plus y square minus 2ax is equal to 0. This circle can also be represented in polar coordinates by the relation r is equal to 2a cos theta. The region can be described easily in terms of polar coordinates as 0 less than or equal to r less than or equal to 2a cos theta minus pi by 2 less than or equal to theta less than or equal to pi by 2.